Hello, good morning, everyone. Welcome to the 45th edition of Crypto 2025. We are very happy to be here and looking forward for a week of full of cryptography. So let's start with these opening remarks. So first of all, as you all know, Crypto 2025 is a hybrid conference. We are offering both in-person and remote access to the main program, and all talks will be live streamed in real time and recorded for later viewing. Please note that remote attendees will be able to watch the presentations live, but will not have direct interactivity with the audience. The reason why we took this decision is because of the somehow difficult political situations that we have sometimes for visa process and to enter in this country. So more on that in this slide. Let me give you some numbers. So we are happy delighted to host 400 delegates in total, but this number is growing as we speak. 226 are regulars, plus 174 students. Besides that, we have also 50 delegates online, 38 are regulars, plus 12 students. So basically 450 people will be attending this crypto edition. And as you know, we have a record number of accepted papers, 156, that really pushes the limit of what we can do with 3 parallel tracks. So yes, if you are wondering why only you only have 20 minutes for presenting your paper, it's because we have this many beautiful papers accepted in crypto, 156 in total. We are also happy and fortunate to have supported 70 student speakers. I'm sure that I'm seeing right now very brilliant faces that are going to present their papers. They are student speakers, and they were supported through the IACR program. On the top of that, we also gave student stipends, and that was thanks to the generous donations of our sponsors, and we awarded 34 student stipends in total. Well, talking about events, we will have lunch every day from Monday to Thursday, always in De La Guerra Dining Commons. The only thing that you need to do to enter there is to show your badge, make sure that you have your badge. And the lunches are always going to be from 12:30 to 2 p.m. The receptions, there was one yesterday in Anacapa Loan, and we will have our dinner, our conference dinner today also in Anacapa Loan. That's going to happen today. Then tomorrow, on Tuesday, we will have the ROM session. Later, we will talk more about this. And the IACR award ceremony. This is going to happen here in the Corwin Pavilion. On Wednesday, we will have our traditional beach barbecue. This is located in Goleta Beach, and is about 10 to 15 minutes walking distance from here. It's going to start like 5:30 p.m. right after the IACR membership meeting, but you have plenty of time to get there to have a pleasant promenade and get to the Goleta Beach. The food there will be served around 5:45 p.m. So no worries about that. When that barbecue finishes around 7:30 p.m., you can come back to the Anacapa Loan and then have our traditional crypto cafe with delicious gelatos, so don't miss it. Talking about our auditoriums, this edition of crypto, we will have brand new auditoriums from the UCSB. They are called the Interactive Learning Pavilion rooms. And we will be using room 1101 and 1302 for most of our sessions, together with this one, with Corwin Pavilion. So we will have these 3 as our main auditoriums, and with only one exception, the MCC Theater, that is a traditional auditorium for crypto, for previous editions of crypto. In that pavilion, in that theater, sorry, MCC Theater, we are going to have only one session on Tuesday afternoon. The Advanced Encryption 2 session will be held there, and all the others in Corwin, ILP 1111 and ILP 1302. And the UCSB staff asked me to remind you that these ILP buildings, they are equipped with neutral gender bathrooms. Talking about the code of conduct, well, the IACR is committed to providing an experience free of harassment and discrimination. So if, unfortunately, any one of you happen to have something to report, please do not hesitate to contact our committees. Our president is Tol Robin, the Code of Conduct liaison, but also you can contact Alison Bishop, that is somewhere here. She is the ethics committee chair, among other many things, and you can also contact me. Rest assured that if you have something to report, we will treat that report with maximum confidence and privacy. So don't hesitate to reach out if this situation happen. And with that, I will give the floor to our program chair, Yael Kalai.
Hello. Hi, guys. Great to see you. Let me first start with a huge thank you to all of you for sending us such amazing papers. As Francisco said, we accepted kind of the maximum we possibly could because your papers were so good. So thank you so much. And I'm really looking forward to hearing about them more in your talks. We gave 3 best paper awards listed here. Joel Gartner got not only best paper, but also best student paper. And we're very much looking forward to hearing more about them in the best paper award session. Also, for our invited talk, we're hosting Nicola Caldrini. He's the expert in machine learning and security. And hopefully he'll convince us all why we as cryptographers are needed to help solve problems, security issues with that come up in machine learning. You have it? Okay, great. So as Francisco said, the rump session is being held tomorrow. Submissions are due tonight at 10 p.m. So please, if you want to give any rump session talk, send your submission today at the submission site, and the slides are due tomorrow at noon. And as it said, we have Alison Bishop and Azalee chairing it. So it should be a lot of fun. For those of you who do not know, Alison Bishop is like really an amazing stand-up comedian. So we expect to laugh. It'll be fun. Okay, next. So there's a woman in cryptography lunch happening tomorrow as well. So if you're here at Crypto and a woman want to join, you're very, very welcome to. And contact these people if you have questions. And let me just end by a few comments or remarks. So we have a few changes to the schedule. So the most up-to-date schedule is the online one, not the printed one. But let me just say the main changes are actually just in the order within sessions. So all the remote speakers are now at the end of the sessions. And then there's only one additional change of someone who missed their flight. And so we're kind of shifting that around. But basically, it's pretty similar to the printed schedule. But there's some fine tuning in the online program. So please look at the online program if you want the exact program. Also, unfortunately, we do not have Q&A for the remote talks due to some technical difficulties. So for the remote talks, if you have questions for the authors, please just email them. And lastly, if you are a speaker, do not forget to send your slides as soon as possible to the link that you got on your email. Is there anything else I'd say? Okay, thank you very much.
Thank you. Thank you, Yael. Yeah, and then I would like to continue with our sponsors. You know, we cannot organize a conference like this without a lot of help from many people. And I would like to start with our sponsors. The platinum sponsors is AWS and Google. Our gold sponsors are MongoDB and Apple. And we have 5 silver sponsors this year. And we have three bronze sponsors, this year. So we are very happy. So let's give them an applause for their donations. And also, I would like to have some words of thanks to many people that made this conference possible. If you have a look on this slide, it's as diverse as it gets. I think I wouldn't like to say that it's the most diverse ever because crypto has a long tradition, but there are a lot of people from different regions and genders and etc. So I would like to thank, of course, our program chairs, Yael and Seny, our ROM session chairs, Alison and Asa, our affiliated event chair, Sofia Celi, our sticker chairs, more about that in a moment, Maria Corte-Real Santos, Jonathan Comada Erickson, and Brian Reinders, our Women in Crypto chair, Marilyn George, our PowerPoint karaoke amazing chair, Alison, and our logo and t-shirt designers, Nareli Cruz Cortez and Ana Iremi Rodriguez Cruz. Also, this wouldn't be possible, this conference, without the strong help and support of the IACR board. I would like to thank Michelle Abdallah, the IACR president. I would like to thank very warmly our IACR treasurer, Brian Lamacchia. He really does a lot of things. The same goes for Bertram Pottering, our membership secretary that solved so many issues that we had with the registrations. Of course, I need to mention Kevin McCurley, who is doing everything for the IACR infrastructure, and Kay McKelly, who is our IACR webmaster. And then the UCSB staff, the director, Whitney Morris, and her team, and Erico McDonald and her team that are in charge of the amazing food that hopefully you guys are going to enjoy during the conference. And I also want, last but not least, to mention our Zoom squad composed by UCSB students, grad students that are doing an amazing job: Jonas, Sender, Luke, Mike, Vicas, Lawrence, and Jose Salazar from Tauman. Then the last words that I want to say is that we have, as is tradition in crypto, we have a game. It's called the sticker game. You should have gotten this board with your swag, and your task is simple. It's just one simple rule: collect all 9 stickers to complete the board. And for the 3 first attendees that show us this board with all the 9 stickers, they will get a small gift of appreciation. The first 3 that get this. And these stickers are going to be given away in different events of crypto. So if you want to collect them all, you need to attend all our events, including this one. This is where we are giving the first sticker. And if you want a hint, even a more powerful hint, then this slide can give you that hint. Thank you very much, and enjoy Crypto 2025.
Okay, let's get started. Hello, everyone. Welcome to the first session of Crypto. So the title of the first talk is How to Model Unitary Oracles, and the talk will be given by Mark Gentry.
All right. Thank you for the introduction. Yeah, so as many of us know, unitary operations are the workhorse of quantum algorithms, and therefore also of quantum cryptography. So for this work, I started with a handful of questions. So one is, what does it mean to efficiently implement a unitary? And what's interesting is that despite quantum computing being a field for now decades, this seemingly fundamental question has not received a lot of attention. There has been some attention recently, but really I think we're still in the phase where we're trying to figure out what this means. What does it mean to efficiently implement a unitary? All right, a related question is, how should we model query access to efficient unitaries? Queries are a fundamental thing in computer science generally, as we think of subroutines as things that you can query. And they're also critical for cryptography because we often have constructions that are black box and make queries to underlying primitives. And our reductions are also often black box in that the reduction takes the adversary and treats it as a black box in order to solve whatever underlying hard problem. So this leads to the natural question of what is a black box unitary for the purposes of black box constructions and reductions, and in particular, what should a black box separation look like? All right, so we take a stance in this work that may be slightly controversial, at least unconventional. So our first claim is that what it means to efficiently implement a unitary is that your unitary has a small quantum circuit where the circuit actually implements that unitary, even including global phase. So global phase is something we usually ignore because it doesn't affect the statistics of a quantum system. But I'm going to take the position that we actually should pay attention to it. And also, I won't really get into it in this talk, but you really should approximate your unitaries to within exponentially small error. In quantum, we always allow some amount of error, but it really should be exponentially small. Okay. And then the other bit that I will talk about is that when we're talking about black box constructions and reductions and impossibilities of these, we should be allowing for controlled operations. So controlling basically means you can be in superposition of having made a query and not. And inverses. This means, quantum is reversible. So we should model our unitaries as such, allow you to actually query the inverse. These two are pretty standard, not universal, but pretty standard in the literature. But we take things a little bit further and we say, well, actually, also you should model conjugates and transposes. And these are kind of weird things. Conjugate basically means you replace I, the square root of -1, with minus I. Why on earth would you do that? We'll discuss it a little later. And transpose is just the conjugating the inverse. So that's kind of naturally follows. Okay, so let's discuss these one by one. So first, why should we allow controlling and inverses? And well, it's because we can easily accomplish these. If you have a circuit that computes some unitary, you can control it just by controlling each gate. And you can do the inverse just by inverting each gate and reversing their order. And these two procedures are very common throughout the literature. I've listed a few examples on the slide. But even here, there's a little bit of a nuance in that has to do with the controlling. So yes, it is true that if your Q implements a quantum circuit and you control each gate, you will implement the controlled version of Q. However, we typically ignore global phase when we're talking about implementing a unitary. And if you ignore global phase, then controlling actually doesn't quite work. And the reason is that if you have a global phase on your unitary and you control it, that global phase turns into a relative phase and you actually get the wrong unitary. And this is really inherent with kind of the existing way that people treat unitaries because, again, we ignore global phase. So really, if we want to be able to carry out controlling on a unitary, we need to either have our circuit actually match the global phase, or at least we need to know what the global phase is. And so for the purposes of this paper, we will take efficient implementation to mean at least you know what this global phase is. And once you do that, then you actually can control straightforward. Controlling gate by gate introduces this relative phase, and then you just correct the relative phase at the end. Okay, so so far everything, this is basically standard stuff in the literature. But the observation is that, well, just like we can control and we can invert by performing these operations gate by gate, we can actually also conjugate and transpose in more or less the same way by conjugating gate by gate, transposing gate by gate. In the case of transpose, we have to reverse the order. So this is, we're going to advocate for allowing these when we're modeling our black box access to unitaries. But this leads to a question, just because we can model the conjugates and transpose, should we? Does it really give us anything to do so? And the point of this work, or at least one of the points of this work, was to give some formal evidence that we really should take these into account. So here I'll just, I can't have not nearly enough time to actually get into any of the results in detail, but I'll just give a high-level overview of some of the things we show. So one, if we're talking about black box separations, first, black box separations just, they depart from reality, right? In reality, your hands aren't tied. You don't have to treat your underlying construction or your adversary as a black box. So we're departing from reality. But because we can implement controlled inverse conjugates and transposes in the real world, if we want our model for black box separations to reflect the real world as closely as possible, then we should model these. And to add a little bit of a formal flavor to this statement, we do prove a theorem, which asks the following question: can you construct a unitary oracle from a classical oracle? For example, later in this session, we'll actually see results using a Haar random unitary. A natural question might be, can you construct a Haar random unitary from a random oracle? Or for the purposes of black box separations, we have many separations relative to unitary oracles, and there's a natural question of if we can upgrade those to separations relative to a classical oracle, because this is widely believed to be more natural or more meaningful. And our theorem is that you can't do this generically. You can't construct a quantum algorithm generically, a quantum oracle generically from a classical oracle in some formal sense, unless your quantum oracle allows for inverting, allows for conjugating, and allows for transpose. There's an annoying caveat that this actually doesn't apply to controlling, but so it doesn't help justify that part, but at least this theorem helps justify why we want inverses, conjugates, and transpose. Okay, and roughly the intuition is that these are operations you can perform on a classical oracle, so anything you try to build from the classical oracle will also allow you to do these things. Okay. Okay, and then for black box reductions for the adversary, we give another result that says that under certain admittedly contrived conditions, you can extend the length of a pseudo-random state generator. I'm not going to define what that is. You can extend the length by 1 qubit. And extending the length of a pseudo-random state generator has been this open question that we've had now. And what we show here is that under some really artificial restriction, you can actually do this. And what's interesting for us is that this only works, our construction can only be proven secure if you're allowed to conjugate the adversary. So in the reduction, you're actually going to make queries to the adversary, both without conjugation and with conjugation. And so this really justifies, or at least makes some attempt at justifying that you need to handle, or you need to allow conjugating your adversary if you're going to try to reason about barriers to proofs, security proofs. Our next result looked at a particular construction of pseudorandom unitaries. So a result from earlier this year showed how to construct pseudorandom unitaries from basically pseudorandom functions using the CPFC construction. And an interesting question is, if we replace the underlying pseudorandom functions with random oracles, could we turn this construction of a pseudorandom unitary into a public random unitary? So pseudorandom unitary, there's a key, and only the person with the key can evaluate it, and it's indistinguishable from a random unitary. A public unitary is one that anyone can evaluate. And you can think of this question as kind of an analog of, can you construct an ideal cipher from a random oracle, but this is the quantum version of it. And a natural place to start answering this question is to look at this CPFC construction and see if this can actually allow you to construct a public random unitary. And we show some barrier to this. So a seemingly necessary first step, based on our earlier set of results, is that in order to build a public random unitary from a PRF or from a random oracle, you really need to be you really need that that what you're building is really a PRU from a PRF that is secure against conjugation, inverses, and transposes. Like, you need to solve this problem first before you can go all the way to constructing a public random unitary. And we show that at least some instantiation of this construction does not satisfy this strong security property. So if you're trying to build a PRU that's secure against conjugations, inverses, and transposes, then this CPFC construction actually does not work, at least if you're doing this binary phase version of it. Our attack doesn't work if, when you go beyond binary phase. Okay, so this puts some barriers on how you might try to construct a public random unitary. All right, so so far we've been talking about these four operations: controlled, conjugate, inverse, and transpose. And the question is there anything else? You know, we already said, hey, you know, maybe the literature has missed conjugation, transpose, or not studied them enough. Maybe we're missing something. Maybe there's still something else out there, and we should really talk about that as well. And we show that actually there's kind of a natural stopping point at these four operations, and you probably, or you don't necessarily need to look beyond them. So formally, our observation is that controlling and conjugating are homomorphisms on unitary. If you take a unitary and you construct this controlled version or the conjugated version, that's a homomorphism. And likewise, transpose and inverse are anti-homomorphisms, which is it's basically a homomorphism, but on the output, you reverse the order when you multiply. And the point is that the reason that we can implement these operations on a quantum circuit is exactly because of this homomorphic property, right? So we can implement these homomorphisms because we can do it gate by gate, and that's exactly what a homomorphism allows us to do. Right, so then the natural question is, are there any other homomorphisms? Right, homomorphisms really naturally lend themselves to efficient implementation. Are there any other homomorphisms or anti-homomorphisms except for these four? And the theorem we show is more or less, no, this is it. So if you consider a homomorphism that is continuous, that is the entries in the matrix representation of the homomorphism are continuous functions, it's hard to imagine a natural, efficiently computable unitary that isn't continuous. So if H is a continuous homomorphism, then one of two things must happen. Either the homomorphism can actually be implemented through a polynomial number of queries to the controlled U or controlled U star operation. So, you know, if it's efficient, then it's actually reduces to just querying the controlled U and controlled U conjugate. Or actually H is inefficient, with the caveat that it's inefficient as long as you're using ancillas. So ancillas are just private workspace of quantum computation. Most interesting algorithms use ancillas in some way or another. And if your algorithm uses an ancilla, even a single bit, if it even has a single bit of workspace, then any H that's not constructible using polynomially many queries will just be inefficient. So there's nothing else efficient except for controlled U and U star. And this leads us to our final result. Is a little bit out of the main theme, but it kind of inspired by this last bit on ancillas, which is to look at ancilla complexity as an interesting notion of complexity. And we show this following interesting result, that if the polynomial hierarchy is not contained in BPP, so this is a purely classical complexity theoretic conjecture, then we show that there is a family of quantum circuits that can be computed efficiently with two ancillas, so just 2 bits of workspace, but can't be computed if you have no workspace. And the rough intuition is that determinants are actually homomorphisms. And if you don't have ancillas, you can actually compute the determinant of a quantum circuit and everything works out. And this allows you to do interesting things. But if you have even a single bit or 2 bits of ancilla, you're completely and utterly incapable of computing the determinant, owing to our previous theorem. And what's really, I thought was kind of interesting about this is that we're deriving a quantum complexity theoretic separation from a purely classical complexity theoretic separation. I thought that was interesting. And that's all I have to say. Thank you.
So we have time for questions.
do they go through with, with controlled access? I mean, one could go through the list of all quantum complexity.
Yeah. Controlling is usually not a problem.
And the conjugate and
Conjugating, I'm not aware of anything where it's a problem. That requires more careful checking. Controlling almost always is fine. And as far as I'm aware, conjugation is
which is
fine
probably
too.
checked even, right? I mean,
Yeah.
the transpose seems weird, and that, anyway, yeah.
Yeah. Oh, I mean, transpose is just the composing inverse and conjugate. So it's
Right.
once you have conjugate, it's no weirder than conjugate.
Right. But as far as you're aware, all these quantum complexities.
They should, though it does require effort to actually go through and make sure that nothing goes haywire.
Okay, so we have time for one more quick question, if any. Okay, if not, let's thank Mark. Okay?
Thank you.
Everyone, I'm Eli.
And maybe let me introduce Eli. Okay, so let's start the second talk. Title is Translation between the Common High Random State Model and the Unitary Model. And Eli will give the talk.
Yeah, everyone. So this is joint work with our previous speaker. So I'm going to be talking about oracle separations in the quantum setting today. And so I'm going to start by just talking about oracle separations in general. What is an oracle separation? So first, what is an oracle? An oracle in the classical setting is just some arbitrary, inefficient, possibly, function on strings. So think a random oracle. And we say that a primitive exists relative to some oracle or in some oracle model if it exists in the world where all parties have query access to the oracle. That is, if there is a protocol implementing the primitive, which is secure against adversaries that have query access to the oracle, where the protocol can also query the oracle. Okay. And so in the random oracle model in particular, we know that one-way functions exist. Random oracle is just a one-way function. But also key exchange is impossible. And so what this means is that there is no construction of key exchange from one-way functions in a way that works relative to the oracle. In fact, this rules out a number of black box techniques for building key exchange from one-way function. So in general, an oracle separation then between primitive 1 and primitive 2 is just going to be some oracle under which primitive 1 exists, but primitive 2 does not. And these are useful because they rule out black box techniques for constructing primitive 2 from primitive 1. So in the quantum setting, we also have oracle separations. But once you're working with quantum cryptographic primitives, you need to somehow model quantum access to the oracle and quantum oracles and all these things. And there are a number of different models of various strengths that give different oracle separation. And I'm going to quickly run through 3 different types of oracles in the quantum setting, not including the conjugate and transpose oracles that Mark talked about in the last talk. Okay. So the first model I'm going to be talking about is just the quantum version of classical oracle separation. So these are oracles that model some classical functionality, so any functionality on strings. And the only difference is now you allow all parties to make quantum queries to this oracle. If you don't know what that means, it's not super important for the rest of this talk. But oracle separations under a classical oracle are kind of the best we can hope for. these rule out any black box constructions of primitive 2 from primitive 1, even if the construction and the reduction are making quantum queries or doing quantum operations on the The next type of oracle separation that is used very commonly are unitary oracle separations. So these are just oracles that implement any quantum functionality, any quantum unitary. And just like any quantum circuit, you can take the inverse of the circuit. We would like all parties to be able to take the inverse of the quantum operation. And so in a unitary oracle setting, we give all parties access to the inverse of the unitary as well as forward access. And unitary oracle separations rule out most black box techniques, not including conjugate and transpose, as Mark just talked about, but still fairly strong. And finally, the third type of oracle I'm going to talk about is something that's a little bit weaker. It's a state oracle. So a state oracle implements the following functionality. It takes in no input and just outputs some fixed quantum state. So the most common example of this in the literature is something that is called the common H-random state model, or the CHRS model, where the oracle will take in no input and then just output a fresh copy of some fixed H-random state. So you can think of this as kind of like the common random string model in the classical setting, but instead of having some fixed random string floating in the air, it's some fixed quantum state. But this is somehow much more powerful than the common random string. And so in particular, one thing to note about the CHRS model is that this map, constructing a random state from nothing, is not actually a invertible map. At least in this model, there's no way to unconstruct a state. Once you've created a state, it exists. You can't just somehow delete it from ever having existed. And so what this means is that oracle separations under state models rule out black box constructions which do not run the primitive in reverse. And this might seem like an esoteric quantum operation, but actually running the primitive in reverse is a very, very common technique in quantum crypto and is used in a number of constructions. Probably or one such construction is like round collapse theorem for quantum commitments. But yeah, so this is a little bit upsetting that this oracle separations work this way, but that's how it is. So let me do a quick run through of the 3 different kinds of oracle separations. So classical oracle separations are kind of the best we can hope for. Unitary separations, the general consensus in the community is that these are good enough. Maybe not the best we can hope for, but they're still, ruling out a number of techniques. And finally, state oracle separations are kind of a preliminary result. They're a good start. They do rule out some techniques, but maybe not as general as we would. But nonetheless, we actually do have a number of results, a number of separations in the common H-random state model. So in particular, we have that one copy pseudorandom states, which are a notion of quantum pseudorandomness, exist in this model, as well as quantum bit commitments. So commitments with quantum communication also exist in this model, and a number of other primitives. But at the same time, polynomial copy pseudorandom states, which are a stronger notion of quantum pseudorandomness, do not exist. And also, all classical communication cryptography does not exist in this model. So one-way functions don't exist. Key exchange with classical communication and quantum parties does not exist, yada, yada, yada. And a number of other things do not exist in the model. And so this means that we have a somewhat weak black box separation of the primitives on the right from the primitives on the left. Okay. But note that this is a state oracle separation, so it doesn't rule out running the primitives in reverse. So we might ask, hey, we have all these separations. Do these also work in some unitary model? Is there a unitary oracle under which we get all the same separation? And 3 works have tried to actually study this question in the past. So each of these works, they defined some unitary oracle and then tried to show that separations in the CHRS also work under this unitary oracle. These first 2 works defined the unitary oracle, which we will call the swap oracle. And so how this oracle works is on input 0, outputs the H-random state, and on input the H-random state, output 0. So this is just the natural unitary version of the CHRS model, in that it comes pre-programmed with a way to unconstruct H-random states. It's given a random state, you can apply this unconstruct operation, which is just the map again. And this third work defines an oracle, which is a bit more complicated, which I'll call like a subset swap oracle. But I'm not going to go into the details of how their separation. So these first two papers tried to translate some separations of the CHRS, two separations in the swap oracle. But unfortunately, there were some bugs in these proofs. This is very tricky to get oracle separations right. And so the proofs actually break down. But the bottom result does in fact work. These separations are good, but slightly more complicated and not fully general. So not all separations in the CHRS, at least, are obviously translated to the subset swap oracle. So we might hope that, hey, these first two papers, they defined this really nice oracle. Their proofs don't work, but maybe we can recover it. And in fact, we could even conjecture that really all oracle separations that hold in the CHRS should also hold in the swap model. So this was our conjecture going into the work. And so in particular, the theorem you would want to prove is that a primitive exists in the common random state model if and only if it exists in this unitary swap model. So what do we show? Well, we show that one direction of this is fine. If a primitive exists in the common random state model, then it also exists in the swap model. This is perfect and very easy to use. On the other hand, if a primitive exists in the swap model, we cannot show that it exists in the common random state model, but we can show that it exists in some related model, which we will call the CHRS minus. So this is a very similar model to the CHRS model. And in fact, most proofs in the CHRS also work in the CHRS minus. And in fact, also these theorems generalize to all state oracles, but I'm not going to talk about that in depth here. So just for the purpose of this talk, we'll focus on the CHRS, but it actually works just with whatever state oracle you want to use. Right. So then what is our template for translating separations in the CHRS to separations in the swap? So let's say you started with some separation in the CHRS. That is, primitive 1 exists and primitive 2 does not exist. Our first theorem says that for free, you can get primitive 1 exists in the swap oracle. And our second theorem gives some sort of template for adapting the proof that primitive 2 does not exist in the CHRS model into a proof that primitive 2 does not exist in the swap. So how does this template work? So to start getting into this, I'm going to first define what the CHRS minus model is that I was talking about before. So for any quantum state phi, you can define a state phi minus, which is just 1 over root 2 ket 0 minus ket phi. So this is essentially the state that has half its weight on 0 and half its weight on phi with a negative sign. Then the CHRS minus model is going to take in no input. It's going to be a state oracle that will just output phi minus for some fixed random state phi. This is very, very similar to the CHRS model, but now instead of outputting phi, we output phi minus. Just replace phi with phi minus. So note that this is still a state oracle. And so in particular, many of the techniques that work in the CHRS model will also work in the CHRS minus model. So how do you use this? So let's say you have a primitive that does not exist in the CHRS model. You can usually, somewhat easily at least, adapt the proof into the claim that that same primitive does not exist in the CHRS minus model. And then our theorem says that you get for free that it does not exist in the unitary swap model. So actually, you can just work with state models to get results in swap models, in unitary models. And state models are generally much easier to work with. Okay, so I want to give a very little bit of technical detail. So one key component in the proof is actually that you can compute the swap oracle using just queries to the CHRS minus oracle. And this is kind of a technique that came from this BMM plus 25 paper. And so what is the swap model? What is the swap oracle? Let's take a little bit, let's take an example of what the swap oracle computes when you actually apply it to phi minus. So if you apply swap to phi minus, this is swap to 1 over root 2, 0, minus 1 over root 2 phi. It's going to swap 0 and phi. And you'll end up with 1 over root 2 phi minus 1 over root 2, 0, which is exactly -1 times phi minus. Okay. So in particular, the swap oracle is actually exactly the map which sends phi minus to -1 times phi minus, and vice versa. So this is known about as like reflection around the phi minus state. So swapping 0 and phi is actually the same as reflecting around phi minus. And using previous techniques, we know that given many copies of a state, you can implement reflection around that state. And so you can implement the swap oracle by just querying the CHRS minus oracle many, many times, getting a whole bunch of copies of phi minus, and then using this to implement reflection around phi minus, which is exactly swap. Okay. So then we have these theorems. We have the template. We then started to apply it to the existing separations in the CHRS minus, or in the CHRS model. And in fact, we were able to show that at least every single separation that I know of in this model just also works in the swap oracle. So this is a generic template that works generally. I would expect that at the very least, the vast majority of separations you can prove in the CHRS will also hold in the swap model. So if you want to work on oracle separations in state models in general, this is actually usually fine, and it is not that hard, at least using our techniques, to translate them to unitary model. So I'm going to conclude with some open questions. So our existing theorem says that if a primitive exists in the CHRS, then it exists in the swap, and if it exists in the swap, it exists in the CHRS minus. You might ask, hey, is it actually necessary to use this minus? So we don't have a counterexample, but we don't have a proof. I personally suspect that it is not possible, but I don't know for sure. And the key component that's kind of missing is that you would really like to have the following theorem. If you have a primitive which is secure in the CHRS minus model, where the primitive makes oracle queries to the CHRS minus model, can you use this to construct a new protocol, p tilde, which is secure in the CHRS? I note that you will need to do a new protocol because the p tilde will not be able to actually query the CHRS minus oracle directly and can't necessarily construct this. And in fact, there's no candidate construction that I can think of. I guess there kind of were in the past, but these do not work. So yeah, this is a cool question. Whether this is possible or not, I don't know for sure. My guess is no, but I think it is worth considering. The second open question I'm going to present is that what about relationships between other quantum oracles? So this is kind of the first paper that explicitly talked about indifferentiability, which is the equivalence in some sense between various quantum oracles. But I think this is a fairly open space. There are a lot of different types of quantum oracles that exist, like Haar unitaries and the quantum random oracle model. And it would be nice to see what are the connections between these. Do separations in one translate to separations in the other? Do constructions in one translate to constructions in other quantum oracles? There are many, many questions here. Yeah, thank you.
So questions for Eli?
Exact. So that doesn't.
So it does. The error. So yeah, this is kind of why I had stars on the theorem statements. The error is arbitrarily inverse polynomial, and so
in the number of copies.
yes, but so for our theorem statements, I guess here, like you can choose what error you want by just taking more copies.
Right.
And so this is usually good enough.
Okay. Right. Thanks.
Okay, so we have time for one more quick question. So maybe can you, Eli? Maybe can you comment on like whether this can be extended to include in the country control and the conjugate oracle, like what Mark said?
Yes, I've started thinking about this. So in general, Mark's paper also has this theorem that if you have like a Haar random state and you have conjugate copies of the Haar random state, this is indistinguishable from just two different Haar random states. I would expect that similar techniques will allow these theorems to work in the conjugate and transpose settings, at least for the case of Haar random states, so in the CHRS. More generally, I think it might be a bit more complicated. I'm not certain it will work.
Okay, so let's thank Sely again. So let's start the third talk of the session. So the title is Pseudo-random unitaries in the Haar random oracle model by Prabhanjan, John, Aditya, and Yao Ting. And Aditya will give the talk.
Thanks for the introduction. So this is a joint work with Prabhanjan, John, and Yao Ting, and we'll talk about pseudo-random unitaries in the Haar oracle model. Since the introduction of quantum pseudo-randomness, we've found multiple applications in multiple fields, from studying wormholes and black holes in an ADS-CFT correspondence in physics to lower bound in quantum learning theory, and multiple applications in complexity theory and cryptography. And one of the most central primitives for this pseudo-randomness is pseudo-random unitaries. So how do we define these? Pseudo-random unitaries are efficiently implementable circuits that behave like Haar random unitaries. So formally, they need two properties. First, we need efficient implementation. So given a key k, there is some polysize circuit gk that maps n-qubit states to n-qubit states in a unitary fashion. And second, we want pseudo-randomness. So any QPT adversary should not be able to distinguish whether it's given access to GK for a random key K or a Haar random unitary U. There's also this strong pseudo-randomness, strong pseudo-random unitaries, where we define pseudo-randomness as adversary being given access to GK and its inverse, and it shouldn't be able to distinguish it from U and its inverse. So what do we know about these? JLS introduced PRUs in a 2018 paper. They gave a candidate but couldn't give a proof. Following this, there were multiple papers on some partial results for constructions. And then finally, last year, we had this one paper that proved a construction, which was MS24. And this, they gave a construction that satisfied adaptive queries, which is the most ideal case. And this question of adaptive queries had eluded us for a long time. And to solve this, they introduced something called the path recording framework, which has been very useful since. So why should we care about PRUs? They have multiple applications, starting from cryptography, where they can be used to give succinct commitments to quantum states and multi-copy secure encryption schemes. And then also in other fields, they have multiple applications. Particularly for cryptography, they're interesting because Kreshmer showed this result, which gave evidence towards quantum pseudo-randomness existing even when one-way functions don't exist. So this possibly gives us an alternate, weaker assumption on which we can base cryptography. So now we know that these can exist without one-way functions. So how much do we know about that? We have multiple constructions of pseudo-randomness, but most of them depend on one-way functions. So in particular, we have a bunch of papers, and all these constructions use one-way functions. In the direction of not using one-way functions, we have two directions we can approach this with. First, we can try building them using quantum assumptions. And there's this one paper recently that has tried doing this. But of course, these quantum assumptions are not as well studied as the classical assumptions are. Another potential direction is we can try building these in some idealized models and later try to instantiate these idealized models without one-way functions. And this is where the quantum random oracle model comes in. This was introduced by Bulin, Pfefferman, and Vazirani in 2020. So what does the model say? It says that all parties as well as the adversary get access to a Haar oracle and its inverse. So you start by sampling a Haar unitary U, and then there's a bunch of parties and there's the adversary, and all of them get access to U and U dagger. This is very similar to the random oracle model, where you start by sampling a random function and then all parties in the adversary get access to the random function. So why should we use this model? First, it can be used to model behavior of random quantum circuits. And these random quantum circuits have been used to show multiple quantum supremacy results. And this is a nice heuristic way to analyze these results. It's also a nice abstraction to study black hole dynamics. I don't know much about these, so I won't comment on this. Third, it gives us a nice pathway to get results from PRUs in the plane model. So in general, if you can get a result in this model, you can get a result from PRU in the plane model. For most results, at least there's some way of doing this. And finally, they can show, you can use this model as like a good oracle to get separations in. And one of the open problems that has been in this model since it was introduced is, can you build pseudo-random unitaries in this model? So you define pseudo-random unitaries in this model as follows. The adversary, of course, gets access to the oracle and its inverse. And the adversary also gets access to a construction that can depend on the oracle or a completely independent Haar unitary. And the adversary should not be able to distinguish between the two cases. And a strong pseudo-random unitary case, they'll also get access to the inverse of this construction or an independent Haar unitary. So what's the progress towards this question? So Bulin, Pfefferman, and Vazirani gave a candidate construction for PRUs in their initial paper, but they couldn't give a proof. Last year, there were these two works that made some partial progress towards solving this problem. And that brings us to our results. So we in our paper show that you can get unbounded polyquery secure strong PRUs in QHROM, and our construction makes two queries to the Haar random oracle. Along with this, we give this additional result, which is the strong gluing theorem for Haar unitaries. You can think of the strong gluing theorem as a result that shows how to glue some smaller Haar unitaries together to get a larger Haar unitary. There was another similar result before, which was in SSH 24, where they showed how to do this for only the case where you have forward access to the Haar unitary. We do this when you also have inverse access to the Haar unitary. And combining these two results, we get a nice result in the plane model, which is that you can get PRU shrinking for free in the plane model, key shrinking for free in the plane model. So in particular, we show that if strong PRUs exist in the plane model, then you can always get, generically always get a PRU with short keys in the plane model. This is a nice result because we know how to do this for pseudo-random generators classically. But for pseudo-random states, we have, this question has eluded us for a long time. We don't know if this result is actually true. And previously, it was known from GJMZ22 that if pseudo-random unitaries exist, then just one query secure pseudo-random unitaries with short keys exist. And it's nice that we can show that like a polyquery pseudo-random unitaries with short keys exist in the plane model. And secondly, since we can show that strong PRUs exist in QHROM, then just by implications, we get all the other primitives from most other primitives from microcrypt existing in QHROM. Okay, so on to the techniques. I'll talk about the techniques for proving strong PRUs in QHROM. So what are some potential constructions we can think about? The first construction is one which only makes a single query to the Haar unitary. So there's some arbitrary key-dependent unitaries, AK and BK, and between these two unitaries, you query the oracle. But you can show that on a on a construction of this form, you can apply it on an EPR pair, and due to something called a ricochet property, BK goes to the other side. And then using some information theoretic attack called an OR lemma, you can prove that this is insecure. So a single query construction does not work. The next possible construction is you do multiple parallel queries to the oracle. So instead of doing just one query to you do U tensor S. But you can show that a similar attack works in this case too. The next thing you can possibly do is do 2 queries to U. Between 2 queries to U, you apply some key-dependent unitary AK in the middle. And in this case, you can apply U inverse to either side of the construction and learn AK in the clear. So doing this, you just get AK in the clear and then learn this unitary, and so this also becomes insecure. That finally leads us to a 2-query construction where both the sides are protected. So there's 3 key-dependent unitary, AK, BK, and CK. And between these, you have 2 queries to U. And at least on the face of this, there's no easy way to attack this. And this brings us to our construction, where we set AK, BK, and CK to be 3 polyxes. And we in fact show that you only need to apply these polyxes on some small register, not the whole register, and the construction is still secure. So now we can talk about how to prove the security. To model the adversary, we think of the adversary as follows. The adversary has some work register B, some query register A. The adversary queries the the oracle and the construction one after the other, applying some unitaries in the middle. And we'll call this final state of the adversary row A, where you're taking expectation over U and the key, and then you just look at adversary's final state. The problem with this is this state is very, very hard to understand. And we have had no idea how to deal with this state before. And this is where the path recording framework comes in. So the thing we know about the state, at least, is that due to by Schmidt decomposition, it must have some purification. So there must be some state on an extra register E, which we'll call the purification register, such that if you trace out this E, you get the state, and you get the state again. And now with this psi A, or the purification, you don't have to deal with taking expectations over the Haar unitary. And the path recording framework shows how to work on this, how to achieve this how to get this psi A. So in particular, they show that there exists some unitary PR or some isometry PR, such that if you replace every query to U with PR and every query to U inverse with PR dagger, then the resulting state is close to the to a purification of row A. So in particular, they show this. And what does this PR look like? So PR, you can think of the purification as a database. When you get a query X in the query register, you map X to almost all possible Ys, and you save that you map X to Y in the database register. So formally, it looks like this. There's X and there's a database R, and you map this to a superposition over all Ys, where you save this tuple X comma Y in R, and just take a superposition over these. And we'll call this database the path. This is only the path recording unitary for forward queries, but you can symmetrize this and get this for inverse queries as well. Okay, so we can use this to try and analyze our construction. So let's look at the both cases, ideal and real case. Ideal case, the first oracle is some oracle U1. Second oracle is some oracle U2. If you purify these two separately, you'll get 2 separate path registers. So the purification will look like this: path 1 tensored with path 2. In the real case, you have the first oracle is the Haar unitary U. And then the second oracle is our construction, which is X, U, X, U, X. And now the purification looks like a single path corresponding to U as well as the keys. And so it looks like this path as well as keys. And to try and prove that these two cases are close, we'll show that there's some key simulation isometry that goes from the purification of one side to the purification of the other side. So what do the experiments look like? Well, if you're querying the on an ideal experiment, if at some point you have the purification looking like path 1, path 2, you query the first oracle, that adds an entry to the first path. And you query the second oracle, it adds an entry to the second path. In the real case, when you query the first oracle, it just adds an entry to the first path. Whereas if you query the second oracle, which is the construction, note that the construction makes 2 queries to you, so it adds 2 entries to this path. And somehow these 2 entries are correlated by the keys, which is the key K2 here. And somehow using using some combinatorial structure of these paths, we want to be able to simulate these from the purification of the ideal case. So how do we actually do this? We do this using a query by query analysis. In particular, we show the following. If you take any intermediate state, then on this intermediate state, the following 2 processes should be closed. So the first process is you make an ideal oracle query, and then you do the key simulation, or you do key simulation followed by a real oracle query. And we want to show that these 2 are closed. So more formally, like for the first oracle, if at any point you have a purification path 1, path 2, you do the following. You query the first oracle U1 followed by key simulation, end up with some state 1. Or you do key simulation followed by oracle query to U. These 2 states need to be closed. And we want a similar thing for the second oracle, where U2 followed by key simulation should be close to key simulation followed by querying the construction. And we show this using some combinatorial properties of the path recording. Interestingly, this way of measuring progress in a query by query fashion, you can prove multiple other results that have already been proven in pseudo-randomness literature. In particular, you can prove PFC as a PRU, you can prove the strong gluing theorem and other results. So it seems like this is an interesting way to look at, to analyze pseudo-random constructions from the FOR2. So conclusions and some open problems. So we showed that there is an unbounded polyquery strong PRU in the QH-ROM. There is a strong gluing theorem for Haar unitaries, and combining these, you get key shrinking for free in the plane model. Some open questions is, first, can you get like the super strong PRUs in strong QH-ROM, where just from Mark's talk, we know that we should consider conjugate and transpose queries now. So can you build this using transpose and conjugate query to the Haar oracle as well as PRU? There is no direct attack as far as I can see for our construction, but there's no direct way to analyze this yet either. Second is, can we get an LOCC type result? So an LOCC type result is used to prove black box separations between quantum primitives and classical communication primitives. And an open question is, can you prove this for QH-ROM? And there's some partial results around this where we can prove this for only forward access to the Haar unitary and some specific cases for when you have inverse access to. And it would be interesting if we can get this for the full QH-ROM. Finally, other questions are, can you instantiate this QH-ROM, or how can you instantiate this QH-ROM? And can you build some unclonable primitives in QH-ROM? This is interesting because if you can do this, then there might be a way to build these using PRUs or strong PRUs, which would link the pseudo-randomness and unclonability things in quantum crypto. That's it. Thank you.
Any questions? So maybe let me ask a technical question. So what's the main technical challenge when you also want to include the inverse query compared to your previous work?
Sorry.
So what's the main technical challenge to handle inverse query in this paper?
So to handle inverse queries, I just showed as if you add a query to the path always, but you technically delete it sometimes. And so you have to do this much more careful query by query analysis and somehow link the path to more combinatorial things like a graph and then build this. So it's just interesting to see that this path can be interpreted as much more of a combinatorial object, and that building that was very interesting.
So the approach is the same, but technically this
Technically,
combinatorial argument gets more complicated.
yeah, technically it becomes more complicated.
So I have time for one more quick question, if any. Okay, if not, this thanks Aditya again. Okay, so let's start let's talk. So the title is Succinct Arguments for Batch QMA and Friends under 8 rounds by Rishabh Goyal and Aditya Jain and Shweta Maitra.
I can take it, don't worry.
Great.
Thanks, Alan.
Yeah, and Rishabh will give the talk.
Great.
Yeah.
All right. Thanks everyone for being here. So this is a joint work with my students, Aditya and Shashwat, who have graduated since. And I think Aditya is in the audience, but Shashwat couldn't be here because of visa issues. Otherwise, he would have presented it because he knows the result is in and out. Unfortunately, you guys are stuck with me, but that's fine. Hopefully, I can sort of convince you guys that this is an interesting topic and there are kind of like a lot of interesting questions that are still open in this area. All right, so let's begin with a brief overview of succinct classical arguments. So I've tried to abstract out the quantum part of this talk so that even if you don't have that much of a quantum background, you should be able to appreciate what's really going on underneath all of these things. So in succinct classical arguments, we have our two favorite parties, Alice and Bob. The goal here is Alice has a witness W for some instance X, which is in the NP language, and Alice wants to prove to Bob using very tiny communication that X is indeed a valid witness, or X is indeed a valid instance in this particular NP language. So as we already know that we can formalize this succinctness requirement as saying that the proof size, the total interaction, the transcript size should not be too big. It should be of fixed length. Moreover, to make sure that these arguments are interesting, we require that if X is not a valid instance, then Bob does not accept this interaction. Moreover, we know that starting with seminal work of Killian in the early 90s, that we have 4-round classical succinct arguments for all languages in NP using very simple tools such as collision-resistant hash functions and PCPs. Moreover, we know if we want to reduce the round complexity of these succinct arguments, then there are some barriers if you're trying to rely only on falsifiable assumptions. But if you're okay with heuristics, such as random oracle model, then we can actually indeed design succinct non-interactive arguments in these specific models. And over the last few years, there has been incredible amount of research in the classical setting that has unlocked many different applications in various contexts for these succinct argument systems. So the focus of this work is really in trying to go to the quantum analog of this problem, which is what we call the succinct quantum argument problem. As you can naturally imagine, in the quantum model, we are imagining that Alice and Bob have access to quantum computing capabilities. Once you have access to quantum computing capabilities, you can naturally ask, hey, can I prove more advanced types of relations? For instance, what if Alice here has some quantum witness and it's trying to prove that an instance X is in a QMA language? So QMA is just the quantum analog of NP. That's how you can sort of just really view it. And you can naturally generalize succinctness and soundness appropriately so that this really makes sense. So this is a great problem, but as a lot of us know, or kind of probably most of us know in this audience, that near-term projections for quantum computing, they tell us that probably in any time in the near future, we will not have a quantum computer in kind of like our pockets. We'd only have kind of like access to as kind of like an untrustworthy cloud. So in that case, the question really becomes that can we actually move towards a setting in which the verifier, the client, is only classically powered. It doesn't have any quantum computing capabilities. So the question then becomes that can these be classically verified, these succinct quantum argument systems? And due to amazing work over the last few years, the answer to this question is really yes. that we can indeed design succinct quantum arguments which have a classical verifier. So this kind of like simplifies the problem as follows, that there is no quantum capabilities that Bob requires. And basically that Alice is only the quantum user. It's just, it has quantum capabilities, and Bob can verify this proof of this quantum for this quantum instance using this classical information. So over the last few years, we've actually seen there are many different ways of trying to attain and design these succinct quantum argument systems. So there are kind of like these three popular approaches of trying to design these succinct quantum arguments, but unfortunately, all of them are stuck at one or more barriers. For instance, they either rely on heuristics or they really require a large number of rounds. Fortunately, you can actually sort of just reduce the number of rounds if you try to work in the quantum random oracle model. So it's known that since all of these protocols have this public coin property, by relying on Fiat-Shamir, you can sort of just really, oh, that should not happen. That should be kind of like a smaller thing, but maybe the font is a little bit bad on some slides. I apologize for that. But the point is that you can reduce the number of rounds for these protocols to a single round, making it non-interactive in the quantum random oracle model. That is fantastic. But the real question is that, can we actually sort of just do better if we rely only on the standard model? If we don't have access to heuristics or quantum random oracle, then what can we do? So in that case, so that's basically the main motivation of our work. And I want to sort of compare that with the classical model. Starting with Killian's work, we already know that in the classical setting, succinct classical arguments, they can be designed in 4 rounds, just using correlation, CRHFs and PCPs. Unfortunately, the quantum setting, there is no known equivalent so far. As people know, there's kind of like hardness in sort of just trying to formalize quantum PCPs, and that kind of like brings in the problem of how to sort of do Killian in the quantum setting. The question really becomes that, okay, that can we actually design succinct quantum arguments for even some subclasses of QMA? Is it possible? Unfortunately, it turns out that the best that we have requires at least 8 rounds if you want to rely on completely standard tools, no heuristics. So this really is sort of just brings to the focus of this work, which is that can we design Killian-style protocols for quantum provers with classical verifiers? So with that, I'm ready to kind of like present our results to you, that what we were able to show in this work. So very briefly, we are studying 2 specific subclasses of QMA, which is the batch QMA class and the monotone batch QMA class. Let me briefly tell you what these classes are. So the batch QMA class, it basically says that every instance that I can prove for this particular language, it contains a batch of individual QMA instances, and each witness is a batch of QMA witnesses. And the goal is to try to prove that all of these instances are valid. But the difference is, for succinctness, I only require the size of the proof does not grow within batch size. That's what I sort of just care about succinctness. It turns out that we can generalize batch QMA to a very interesting class called monotone batch QMA, which tries to generalize the notion of AND predicates over all batch of instances to an arbitrary monotone circuit. So this is a classical monotone circuit, basically says, for instance, imagine that half of these instances are valid if you want to prove that. So there is some non-determinism, additional non-determinism that exists in this case. So for these 2 classes, batch QMA, monotone batch QMA, we have interesting results. So first of all, we show that if you're okay with post-quantum hardness of learning with errors, as well as post-quantum hardness of functional encryption, you can design a 4-round succinct quantum argument system with classical verifiers with optimal communication complexity. And if you don't like post-quantum FE, because for that we don't have currently any provable sort of primitives, then you can actually just rely on quantum LWE, post-quantum LWE, but in that case, you would need to pay a large first message. The good news is that the first message can be treated as a CRS. So if you're okay with the CRS, then it's kind of like a reusable first message. So you get really succinct protocol if you're okay with a long CRS. And we're also able to generalize all these results to the batch, the monotone batch QMA setting, in which we're able to say that under LWE, we can get a 6-round protocol with optimal communication complexity. So due to time constraints, I'll probably focus mostly on the first result, how to do batch QMA, but I kind of like implore all of you to look at the monotone batch QMA because it requires a lot of interesting classical ideas that probably people working on classical proof systems could potentially benefit from. I'll try to sort of summarize what those interesting ideas are. But first of all, let me actually go ahead and sort of talk about our first result. So in trying to explain the first result, I would kind of like try to start by giving you the main key barrier that exists in prior works, because of which everybody was stuck at kind of like this high number of rounds. So the key barrier really is to design these quantum arguments, these succinct quantum arguments. All prior works, they did rely on some type of a classical succinct argument for NP. The reason they relied on these things is just because they had to prove some classical strings very succinctly about the quantum protocols. And it turns out the security proof, the soundness proof of these protocols, that relied on trying to take a cheating quantum prover and try to extract some quantum, what I call a pseudo witness, kind of like a pseudo invalid witness, which tells you that, okay, hey, it's a classical witness, but tells you that things are wrong in the quantum setting. And to kind of like really do this, we need to make sure that we require these rewindable or extractable succinct classical arguments. And the dilemma really here is that we need more rounds for doing extraction using these classical arguments because of known barriers. At the same time, we really need extraction of these classical arguments to make sure the proof of soundness in the quantum setting really works. So these kind of like are just butting heads. So our intuition is that can we actually try to get around this barrier of doing this full extraction? Are there some other ideas that we can rely on? So at a very high level, let me first just try to explain to you. Okay, that's fine. I think I had one slide here and that got moved around, but that's fine. I think that should be okay. So first, let me actually tell you what is the kind of like this key rewinding barrier and how this can to be overcome in these particular settings. So first of all, I'm going to tell you some tools. And these tools are what we use to design these quantum succinct arguments in prior works. And they're going to give you the essence of how things are working. And then we can try to see how to solve this problem. So the main tools that I'm going to tell you about are first the FHM protocol. So it's a very well-known protocol. It basically says that both Alice and Bob are quantum parties, but Bob has really limited quantum capabilities. It can only perform a measurement on a proof state and then do some classical computation. So we already have this. The next protocol that I'm going to rely on is what we call the Mahadev's measurement protocol. It's a very popular and very powerful 4-round protocol in which we have a classical verifier, but a quantum prover, a quantum Alice. And what verifier really wants to do is the verifier wants to make sure that it can get measurement results from a malicious Alice without getting any quantum, let's just say, any quantum interaction with Alice. And the third tool, as you probably can imagine, is what we really need here is we need some type of succinct classical arguments for NP. So if you have these 3 tools, and if you just have this abstraction of what these tools are really doing, then it's pretty simple to see how these tools can be combined to design succinct quantum arguments. So next, what I'm going to do is I'm going to focus on the setting of batch QMA and try to just build this protocol. And the blueprint I'm going to rely is on kind of like this beautiful blueprint by Bartosik et al., who gave this blueprint of combining these multiple different objects in doing this succinct quantum argument thing. So the way this works is I have this quantum party Alice. It has a batch of QMA witnesses. I have my Bob. So the way the protocol starts is Bob says, I'm going to send you a Mahadev commitment key as well as a regular hash key. Then Alice says, okay, I'm going to use this commitment key to commit to all my witness states independently, get a classical string that commits to these quantum states, and I'm going to hash them together. I'm going to send you a digest of all these commitments. After that, Alice and Bob, they just participate in this interactive protocol where Alice is trying to prove, hey, I know yi's for this digested value so that I can prove to you I am computing this hash correctly in a nice way. Once this is done, then Bob sends this Mahadev challenge element, which is kind of like a question in a sense. So it poses this question. And then what Alice does here, Alice says, okay, hey, I'm going to do kind of like this test or kind of like a measure type of a thing. And based on that, I'm going to give you the responses. So I'm basically going to open the commitment, give you the commitment openings, but I can't give you all of them. Let me hash them together again so that it's succinct, send you this hash of these openings. And after that, what Bob and Alice can do, they can perform another round of interaction in which Alice can try to prove that I know all these commitments that are hashed together in this hash string. Once all of this is done, the final thing to do is Bob simply sends its private key, which is something that you use for doing the Mahadev style verification. It sends over that private key, and Alice, given all this information, tries to prove that I have the right openings as well as commitment strings, such that everything is really valid. Now, it turns out if these black boxes are implemented using a succinct argument system, a succinct classical argument system, everything is really succinct. But this is really where the problem lies. The point is that if we focus on these 3 steps, that we need to extract the entire sequence of pre-images. All yi's, all zi's, everything has to be extracted from these rounds in order to prove soundness. So because of this particular issue, it turns out we have to add extra 2 rounds in all of these black boxes. And if you try to do a rough counting, then you will really see why does these works rely on kind of like almost 8 plus or 10 plus number of rounds here. So our key insight really is that can we actually go beyond this type of a framework in trying to sort of not use full extraction, but kind of like rely on somewhat of a partial extraction. So really the key insight of this work is to sort of go away from the full extraction model in the quantum setting and try to make sure that partial extraction with straight line extraction properties, that is enough to still prove security in the quantum setting. So at a very high level, the insights really are that we're going to show that full extraction is not really necessary. And what we can do is we can bypass this reminding thing, this reminding barrier, by simply doing straight line, somewhere extraction. And we can also rely on classical objects that we know, say, from assumptions such as learning with errors, which are much weaker than fully succinct non-argument or arguments of knowledge for classical NP. We're going to rely on weaker objects such as batch arguments, which we know how to design non-interactively as well. So with that brief insight, let me tell you kind of like how do we kind of like go about in trying to get around this barrier. So let's just literally look at and again, so for people who don't know, BARGs is basically a short form for batch arguments, and batch arguments are nothing but taking snarks, but restricting it to batch NP class. All right. So with that, let's just look back at the picture that we had before. Alice and Bob are interacting, and they're really trying to sort of do this batch QMA verification. So our intuition really is that look at all these black boxes. Let's just replace all of these things with simply a BARG. You might think, okay, does it really work? If you just look carefully at all of these things, it does really work by just replacing the hash functions with the Merkle tree so that everything has an efficient local opening. So just literally replacing BARGs here, just doing the most natural thing really does work already. And if you now try to count the number of rounds, it reduces the number of rounds to merely 6. So this just tells us that if we kind of like do these things, then we can kind of like merge all of these things, get 6 rounds where we are going to send a bunch of BARGs. The first BARG proves that HY was computed correctly. The second BARG proves HZ was computed correctly. The third BARG proves that FHM was computed correctly. So BARGs are known from learning with errors, and they give us this straight line somewhere extraction property. Combining all of these things, we kind of like get a very simple warm-up theorem, which says that under LWE, we get these 6-round succinct arguments for batch QMA. So 6 rounds is good, we're making progress, but that's not the ideal goal. Ideally, I would really be happy if we can get it non-interactively, but maybe that's a bridge too far. Let's just try to match Killian for now. Can we get 4 rounds? So now a natural thought would be that how can we go to 4 rounds? So one natural idea that people could try is, hey, let's just try to look at what every round is really doing. The first 4 rounds, they're kind of like doing the Mahadev check. And those will always require 4 rounds. We can't get around that barrier. We really need new insights over there. But what about the last 2 rounds? They're just sending a private key and doing some BARG check. What if we simply sort of just send this private key at the beginning? So the idea simply is, hey, send FHE encryption of this private key and let the quantum prover perform all of this computation homomorphically and send a new FHE evaluated ciphertext of the entire computation, as well as a proof that the computation was done correctly. Seems to make sense. And again, this idea is not ours. I'll sort of tell you guys that this idea was already used in prior works, where the goal was to do public coin version of these protocols. So it seems like maybe this seems a good enough candidate for doing 4-round BARGs. But unfortunately, if you try to prove it, then there are a bunch of problems. So let me first tell you the first problem. The first problem is that it's very difficult how you can prove using just plain BARGs that the final FHE ciphertext was computed correctly. Prior works, they were using these snarks, or I should say, interacting like Killian-style arguments of knowledge, so that they can just prove things for general NP. We only have BARGs. And using BARGs, we can't prove an arbitrary FHE ciphertext was computed correctly, because it doesn't have this batching structure. It seems like a issue, but it turns out there's actually a clean enough solution for solving this problem. Our idea is that rather than doing this FHE evaluation arbitrarily, view the entire batch FHE evaluation as an AND tree itself. So draw kind of like a big tree of AND gates and sort of just do these FHE, FHM plus verifications at the leaf and try to combine them using kind of like an FHE AND tree. And then if you have an FHE AND tree, it has the structure of a Merkle tree, and you can sort of just still prove that this ciphertext was computed correctly. The final ciphertext at the root of the FHE tree using these Merkle tree type of openings. And it turns out that at least using this, we can instantiate this 4-round protocol. So we now at least have a candidate 4-round protocol. So next, the question is that how do we prove soundness for this particular protocol? And this is basically where the big barrier really appears. What we see is that the issue really here is that the reduction algorithm must really know the FHE secret key to even check whether the verifier was, the prover was successful or not. So the prover doesn't, or the verifier can't even know whether the prover is successful without getting this FHE secret key, because it has to decrypt this final ciphertext and check that the value is equal to 1 or not, because that denotes whether the prover was successful or not. And the problem is that we want to go to a hybrid in the security proof where the reduction algorithm does not want to know the FHE secret key, but can just do all these checks using just barg trapdoors, or like by doing barg extraction. And this is a really big problem. For experts in the audience, if you sort of think about it a bit more carefully, it seems very similar to why the PCP plus PIR approach failed back in the day, which was kind of like shown by our friends that this PCP plus PIR approach doesn't work because it has kind of like this no signaling problem. Similar problems exist here to trying to prove its security. So this tells us that we have a good candidate, but we don't have a good way of proving security. So our final idea is that, okay, hey, let's just try to get around this problem and use a concept of what we call bootstrapping FHE keys. And the idea really is, and how much time do I have? Actually, have lost track. Okay, I have 2 minutes. So I have just maybe a minute to tell you what the high-level idea is, and then I'll try to conclude. So idea really is, let me actually sort of skip this particular thing. So because this is not useful, let me show you a picture. So at a very high level, we are saying that we can't do this extraction or this FHE move. So we can't move from an FHE secret key to a barg extraction step in the hybrid proof, in the security proof of this particular. So our intuition is that what if we change the structure of the underlying AND tree itself? And what I mean by that is, rather than having the same Mahadev commitment key for every instance or for all the instances, I'm going to have a separate Mahadev key for every instance. So I'm going to have, let's just say, n different commitment keys. I'm going to do FHE encryption under a fresh FHE key. And this is what I'm going to write down at the leaf of this particular tree. Then I'm going to draw some bootstrapping FHE ciphertext where the next level of ciphertext is going to encrypt 2 FHE secret keys for the bottom layers, for the bottom nodes at this level. And you keep on doing it until the end, you basically have this tree of bootstrapping FHE ciphertext. What's the advantage of doing this? The advantage of doing this is that now you can take this protocol, replace that first singular FHE ciphertext, which is a sequence of FHE ciphertext, and then you can still do the appropriate adjustments in the FHE and bar computation step to make sure the protocol really works. But still, there's something magical that why are we really doing it? It does have a disadvantage, but what's the advantage of it? The advantage really is that if you look at the reduction algorithm from the reduction algorithm's perspective, now there are 2 ways of verifying whether a prover is successful or not. Either you can get the root FHE secret key at the top, or you can use a barg trapdoor as well as, let's just say, log n less FHE keys. So if you look at this particular window, I can say I can use a barg trapdoor for checking that this part is correctly done, and the rest I can just use using FHE. So this way we can make sure that the proof really works out, and we can get our final theorem that, hey, just under LWE, we can get 4-round batch QMA, but with the long first message. It can be reused, but it's still long. And I'll sort of just tell you, due to lack of time, I'll just tell you guys that you can actually really compress this using functional encryption on IO by sort of just making sure that the first step that is being performed by the prover, that can be done, or that is being sent by the verifier, can be performed by the prover on its own. So add 1 more level of delegation. And yeah, you can actually even go beyond batch QMA. So let me sort of tell you guys that there are some cool insights over there. I'll not be able to tell you guys about how we solve the monotone QMA problem, but I would really tell you that there is a classical piece that we have to solve in trying to solve the monotone batch QMA problem. Because in the classical setting, the protocols are non-interactive. So you don't have problems due to checking consistency issues across different rounds. When you're doing monotone batch QMA, an attacker could potentially try to cheat by giving you different responses in different rounds. So you have to make sure different rounds are kind of like bound together, they're consistent. So for this, we need to kind of like rely on some new techniques of combining bargs and monotone bargs in a special way, so that proof does really work out. So I kind of like ask you guys to look at the paper. There's some more results, and I'll try to conclude with some open questions, as well as a conclusion of what we do. And just kind of like, I would say that an alternative way of viewing this result is that how to prove soundness of succinct quantum arguments without rewinding. That's basically the main contribution of this work. So thank you very much for listening.
So we run out of time, but we can take one quick question, if any.
Just to make sure I understand. So you said there's like the first bark, the second bark, all you need there is like a sum extractable hash, right? So you only did sum extractable hash for the Ys,
Exactly.
a sum extractable hash for the openings. And then the problem is kind of, is that if you look at what's in there, like the Yi and the Oi of where the bad instance is, you're saying that it may still be incorrect, like bad, even though the cheating prover may have at the end giving you a good bark under the FHE of the trap.
So you mean for the 4 round, right? Yeah.
No, yeah, for the 4 round.
Yeah, exactly.
That's the issue.
Yeah.
That's okay.
Because of this dependence thing, precisely because when you commit to I star, then at that point, everything is committed at that point, and the prover technically could depend upon it, although it's encrypted.
Yeah.
So that kind of like causes a problem that you don't know where to place it. So which is why it's like it has to be long. Probably can be solved, but I don't know. Good problem, but yeah. Thanks.
Great, thank you.
So let's take other questions offline, and thanks all the speakers of the session again. Coffee break.